webinar session which has been arranged by IEEE CTSOC SPS EMBS Joint Chapter UET Taxila PES and PELS Islamabad section. We are honored to have a highly accomplished speaker with us today. It is truly an honor for me to introduce our esteemed speaker, Mr. Rashid Iqbal. Mr. Rashid is currently working as a senior principal engineer at Cadence in the US. He's a former Intel professional with a remarkable 19 years of experience in the United States, specializing in chip design and timing. He is also a proud alumnus of UET Taxila batch of 2000 and the founder of the popular YouTube channel Chip Expert, where he shares valuable technical content for learners around the globe. Thank you, sir, for being here today. Just a little housekeeping before we proceed. This will be a 40 to 45 minutes session, and the last 10 minutes will be reserved for your queries. Now let's give a warm welcome to Mr. Rashid Iqbal as he joins us to share his valuable knowledge and experience today.
Okay, thank you so much for a very nice introduction. Yeah, you guys can see me, right? I can't see myself, so just want to make sure. Right, you can hear me, you can see me, you can see my screen, all three are good?
Yes, sir, we can see your screen.
Oh, okay, all right, okay, I just want to make sure. Yeah, no, it's great. As I said, I'm super excited. It's in the last 21 years is my first time interaction with actually I never had interaction with a group of students since I graduated from UT Taxila. I was in a 1997 session. Yeah, it took us at that time 4.5 years to finish the degree. When we started, it was a lot of student politics and all that, so that wasted some time. But we were still lucky that we finished it in about 4.5 years at that time. I think you guys don't know that what was going on around that time, but anyway, I finished degree in 2001. In 2001, during this time, we had exams, and I still remember we were sitting in a paper in an exam, and it was super hard, and the light went off, and writing on a paper was super hard. I was sweating, and it was very hard. I remember that. Okay. Anyway, I finished uh, that in exam in July. Result came in August, and in September 2001, I started my first job at Enabling Technologies at that time. Company of Dr. Shoaib, who is running Care or Case and those companies right now. So yeah, it's been a while, and I've interacted with a group of students from UT Tech Lab. So um, I can understand some of the things that you go through. I don't know if things are different right now, but yeah, when I was thinking of okay, what I'm going to talk, um, I consider myself where I was in during the years at UT Taxila, and what I knew, what I didn't know, and what kind of things went after that. So yeah, I created this presentation just to give you guys an overview. And I know, what is your name? Ume Abiha. Sorry if I'm pronouncing it incorrectly. Is that correct?
Yes, sir, it's correct.
Okay, so I know you said okay 10 minutes at the end, but when a lot of people are in a meeting, it's when you start talking in audio, it becomes not manageable. But feel free to in the chat box um, uh, give your questions during the call, and you'll feel free to after 5-10 minutes you can read those questions, and because it's important that this is interactive, right? It's not a corporate presentation where you just keep talking, and then at the end, I mean, I wish I was there in person and I could take your question, I could see everyone directly, but try to make it interactive. And my personal attention time is really 20-25 minutes. After, if a presentation gets longer than that, I just lose my interest. So I will try to keep it shorter, and you can ask questions anytime. Okay. So I created, as I said, some content just to give a talk, a direction. And I'm open to having more sessions with you guys. Whenever I say guys, I mean guys and girls. Okay. Um, so, and that's a special thing for UT Taxila. And I really want all of you to understand the importance of chip design, understand what opportunities are out there, um, develop right knowledge in this field if you have interest. And I want to give you some practical side of the things. After master degree, I did a master degree in Sweden at that time. After working 3.5 years in Pakistan, I went to Sweden. I did a master degree there. So after master degree, all my experiences, yeah, I didn't do PhD, so it's all professional experience. So I want to give you that experience, that exposure, which when you are in college or university, you don't have that. You're going through theory, exams, and all that. And I think the biggest trouble is that students are not able to connect their what they are learning to what's going to happen in the field on job, right? The practical aspect of it. Uh, because if you are able to connect it, then it's interesting. You feel passionate about it. But the way things are taught, sometimes, and I used to think exactly the same way. I'm not able to connect the dots between what I'm studying to what I'm doing. Also, our bachelor degrees, not even in Pakistan, but even in here in US, they are very generic. It's become more of a business, right? I think if you really want to be chip design expert, you just need a 1 year, 1 year and a half, and you just study the very targeted courses. But our bachelor degrees and even master is so generic that they're gonna teach you a little bit of everything. And at the end of 4 years, you're not master of anything, or you're not, I mean, we don't expect you to be master, but at least you're not deeper enough into one field, which is a kind of tragedy overall worldwide education because it's more becomes a business than actually thinking what actually students need to know. And the younger generations that who are coming, they're very um, they want to know very specific, targeted things. They have a different way of thinking. So I think our syllabus, our curriculum is still not, even here, US is not tuned to the newer generation needs or demand. So, uh, but I will try to give you that chip design overview. And as I said, definitely cannot. Zhang sent me very good questions. And we can in future sessions go over those. And I cover all my stuff in my YouTube channel, which I will at the end I will give you an intro. But I teach everything there, and you can always follow that. And when we can have some dedicated sessions with you, if you have specific questions in a particular area, so follow there. If you're not, if you have any questions, anytime contact me. All right. Okay. Enough. I can talk for hours, but I will try to be specific on this one. So here, what you see. First, I want to tell you, okay, chips are super important. Why they're important? Um, why chips are, it's a hard field these days. What do you think? Can you write in the chat window why you think chips are suddenly become so hard, or maybe they were always hard? And you can read, if you can read some of the comments. Sorry, if I go back and start reading it, it is gonna, um, I have to change window. I'm on iPad. It's gonna create a disturbance. So, and feel free to write anything. It doesn't have to be the right answer, right? So don't be shy. Can you read some of the comments, if any?
Sir, someone answered because the area is based on IoT
Yeah, okay, IoT.
and embedded systems.
Embedded systems. Okay. Anything else?
And someone else said they're so important because they're using in a lot of things like computer mobiles and many other things.
Okay. Yeah, mobile.
And they're
Your
fundamental to modern technology.
fundamental to modern technology. Okay. What is the hottest field right now for chips? Where the lot of investment is happening in chip designing. Investors are really active in that area, which has kind of revolutionized the chip industry right now. And it was always a hard field. We know chips are in every electronics. They are core part of it, and all the new technology eventually hardwares are made of chips. So chips, you make smaller, more chips, you can bring more capability into more technology. So, okay, we understand all that, but what is that field, the latest, that is changing everything? Is a buzzword. Okay. Do you want to read some more comments if there are?
Sir, someone said that AI is dependent on it. Another said military, power management,
Yeah.
graphics
AI
card.
is the word. Yes. Artificial intelligence. Especially if you look at generative AI, right? AI has two areas. Okay, traditional artificial intelligence, which was machine learning, I would call it. And then generative AI came a couple of years ago, ChatGPT came, right? Large language model. That intelligence is built. So it can generate intelligent information based on your prompts, right? So that has opened up so many avenues for humanity to make progress in the future. And in the generative AI, the key thing is, first is you train those large language models. First step. Second step is, once those are trained, then you do what they call an inference. You give a prompt, you give something, and they will do a real time action for you. Okay, so training and inference. And training is with so much data, right? Those large language models are trained for months using what? GPUs. So lucky for NVIDIA that that was the right architecture when it comes of the training large language model. It's more the data, the kind of structure that was in GPUs for graphics, that was more suitable for that. So, and you can see that how NVIDIA stock went up, and those GPUs are used everywhere. So then people realize, okay, just processing so much data. Now we need a bigger and bigger and bigger chips, more and more powerful chips. So that thing has recently brought a revolution in chip design, so much more focus, because there is no way to process that much data without having so much powerful chips working at the bottom of it. But the thing is that chips are everywhere. Chips, as you said, they are in our mobile technology, right? All the work is done there by chips, computer PCs, servers, embedded system. There is no device these days which is not doesn't have electronics in it, doesn't have some sort of automation in it, right? And the chips are key component there. So when you when you talk about chips, all right. So, what are those different chips that you see there? So, I'm just showing a picture here. So let me take my Apple Pencil. So, this picture here, I'm focusing. So you can see that this is just a motherboard, but it has your CPU core, right? That's the chip. Then you plug in a graphics card here. There is a chip there. Then you put those DDR, SRAM slots, then each individual is a chip, right? So chips can be, now I'm giving you different categories of chips. So chips can be CPUs, Chip can be memories. Okay, chips can be very targeted, what I'm calling accelerator here, this graphic, because this CPU is good for a general purpose stuff, but when you need a dedicated graphics work, this will get so busy, it will not, it will be busy, mouse, keyboard, and other things. Then you need a special accelerator kind of CPU, acceleration dedicated chip that is called offloading the CPU. So those are accelerators there. Now then I can go into CPU stuff, but I'm not going to spend much time. Okay, CPUs can be your general purpose. Using PC, which you can open an Excel sheet, you can work on this VNC, you can have an image, you can and other things that I'm doing, browsing and all that, right? And you can have very embedded one. It could be the one used in a washing machine, in a fridge, in vacuum cleaners, those automated ones. So it can be very specialized, something for military, for example. Memories can be some of the on-chip memory, that's RAM, can be external memory like the one I'm showing here. Okay, chips, I already gave you a little bit background. Then in the chips, sometimes we also have, um, so analog signal comes from real time or real life or something. Okay, so you need to be converted to digital because your chips are predominantly digital. They process what? 0 and 1. Okay, 0 1 1 0 0 1. So to convert that, you need analog to digital converters. Some of those chips, those can be some blocks on a chip, or that can be a separate chip. And then you can have, like, if RF signal coming in, you need to analog and you process that, condition that. So that's called analog front ends. You need clock generation. You need, so your whole digital system works on a clock, right? So clock generation can happen within the chip, but generally an oscillator coming from outside. So you need chips for that. You need chips for generating different type of voltages. So my point is, you can have CPUs, you have memories, you can have those accelerators. This is digital, this is digital, this is digital, but you also need some of these components which are called analog chips or mixed signal. Analog digital when together on a chip is called mixed signal. So you need some of these chips. So I'm kind of giving you multiple diversion here. On one side, I'm saying chips based on the functionality they can be different based on application, but here I'm saying they can be CPU, they can be memories, customized accelerator or analog, these type of special analog functions. But at the same time, the other thing I'm giving you, they are mainly a digital chip, okay, and there are some analog chips. All right. So digital analog is especially important for you to understand. The methodology is a little bit different. But mainly the chip I'm talking about is something that looks like this. Those are the chips that I did at um, Intel, and some of the big chips that I'm seeing in the market, those are something like this. Okay, you have a huge chip. It has so many CPU cores. These can be CPUs, these can be GPUs, or these can be um, or any special CPU, right? You need a lot of CPUs. Why you need CPUs? All right, we'll talk some other time. There's so much I can explain you, but it's okay. Let's focus on a few things. So you have typically CPUs. Those are, you can write software for CPUs. Right? That's the cool thing about CPU. You can make them work differently based on the software that you write, and software is stored in the memory. Okay, then as I said, you need this DDR. This has interface to those SRAMs, DRAMs I mentioned. Then you have a clock circuitry. You have these accelerators. Remember I mentioned some special circuitry that helps CPUs to process data. Okay, then IOs, PCI is used to connect some off-chip interfaces to the chip, high-speed interfaces, right? Could be talking to graphics card. You have general purpose IOs. Some of the IOs you use. Um, we always send out some IOs that are eventually we don't know at the time of chip, but the user can use it for different purpose. There are other kind of IOs like USB, your display, hard disk, those type of things, right? So typically, if you look at a chip, it has a lot of processing units. It has accelerators. It has interfaces, and it has some of these clocks and some other analog components. So it's, you can say that your chip is 90% to 95% is digital, and then small portion is analog. Now, why digital? What is the benefit of digital? Why we use digital? Why? What is the benefit of digital? Any thoughts? You want to read? Any comment?
Sir, someone said less error.
Okay. Mm-hmm. Anybody else?
And good accuracy.
Good accuracy. Okay. Anybody else? Good, good. Keep trying. Yeah, that's good. All right. Nothing else. It's good. I keep asking a question. I just want to make sure you guys are not sleeping. Okay, so the big advantage with digital is everything is 0 and 1, right? In analog, it can be this voltage level, 1 volt, zero point 0.9 volt, zero point 0.8 volt. There are so many discrete values. But with digital, it's 0 volt or 1 volt, 0, 1, 1 volt, 0 or 1, 0, 1, 1, 0, 1, 0, 1, 0. Just think of that. If your all data is 0, 1, processing is simple, it's 0 or 1, right? So, uh, thinking of hardware, creating hardware is simpler because we have simplified it ourselves, even though it's actually a voltage level, but higher abstract is 0, 1. And you guys have studied logic design? How many people have studied logic design? Okay. Anybody? Okay, I see a hand raised.
I have studied logic design.
Say that again.
So I guess most of the students have
Oh,
studied logic.
good. That's good. That's great to know. Okay, I didn't know that. All right, I might ask you a question later on. So this is an Intel chip. This is not a latest one. I think it's Intel. Whenever it creates, or every company, they always have a code name for the chip inside. So we don't call it. I'm working on i5, i7, i9. Okay, we give it a code name. For example, this the code name was Raptor Lake. Um, the Intel chips were for the servers, for the data centers, but some, the major one that you are familiar with are the one used in desktop. So forgot which one, but this is 12 generation Intel core. Sometimes when you're working on something, we don't even know what is its commercial name. So we are more familiar with the Raptor Lake. So Raptor Lake was an Intel chip. It's not a latest chip, 2-3 years older. And just wanted to show you, just wanted to give you an idea of that. So if you look at here, this is the chip. And actually inside, in the package, we have two chips. So for you, when a user looks at it, just one chip. But actually within the packet, they have two chips. And these are all the interfaces it has. So just want to show you what a chip in real time looks like. It has a SATA hard disk, it's got PCI, USB, PCI, this is, I don't know which connection it is. This is DDR, you know, those. This is, what is, I don't know. But the idea is, okay, another PCI. Okay, there's another interface. So it has a lot of interface. Look at this, there's a chip side. But it communicates with the rest of the world. That's where the IOs, and inside it has a lot of processing. And I took a picture of this top chip, this one, and actual layout, it looks something like this. Okay, so it's a pretty big chip. So you can see that this one has some more information. You have CPU cores. So inside there are several cores. Okay, there are core, there are cache. I'm sure you have studied in computer architecture, some of the cache. They also have a different type of cores, you know, smaller core, a bigger core. So this is another. They call, there again, you have these names, Raptor Cove core, Grace Montco. These are the code names used within Intel. Now people are familiar outside. So there is no confidential information about Intel. I'm not with Intel anymore, but I spent 19 years at Intel. So know these things well. So graphics, media engine, and this is where you have some of the other IOs, different structure there. So just to want to give you an idea of how a big chip looks like, right? So how many transistors are in modern chips? The big chips, the something chip I'm talking about. Any guess? All right, you want to read some comments? I'm keeping you busy. I wish I could see you guys. What was the guess? Thousands?
There are
Millions?
millions and billions.
Millions. Okay.
Billions as well.
Billions as well. Yeah, that's true actually. I gave a hint there. In modern chip, there are billions of transistors. Um, I think we are there. It's a different topic. We cannot make the chip too big. There's a limit because eventually there's a limit of how you can do a lithography limit, where we call it what was the terminology anyway? I'm forgetting the reticle limit. There's a reticle limit, but if we make the typical type of chips we have, we easily have 10, 20, 30 billions transistor on those. Okay. So another, I want to tell you the difference between 34 minutes past. So between ASIC and FPGA, this is an important one. Do people know this? Anybody? Any quick answer on what is the difference between ASIC and FPGA? This will give me an idea of my time I need to spend on it. Any volunteer?
Sir, can I answer?
Yes.
Sir, ASIC is like a rigid chip. You can only program it once, and FPGA you can reprogram it.
Okay. All right. Yeah, that's pretty close. Anybody else? I'm sure you all have heard this ASIC, FPGAs, FPGAs. I
Sir,
think it.
someone answered FPGA simple hardware testing of RTL code. Another one said ASIC is design specific, FPGA is reprogrammable.
Yeah. Okay. Yeah, I think you guys are getting closer. So ASIC is the FPGA. Both are. All right. Here's one. Somebody has to design both type of chips. Okay, but once chip is there, the ASIC, the hardware inside the ASIC is fixed. It's done. If it has um, 30 million flip-flops, that's it. 30 million. If those 30 million flip-flops are connected in a special way, it's done. They are connected. You cannot change their connectivity. So the the chip within ASIC is kind of done, hardwired. You cannot change it. The only way you can use it for different functionality is through software, right? So for example, a CPU needs some instruction, and based on instruction that coming from the memory, it can decode them differently, and based on different instruction codes, it can do the different tasks. That is a programmability through software, but hardware is not programmed. Hardware is fixed. All the elements that you need to use, like gates, and gate, NAND, NOR, um, memories on chip, or the flip-flop, they're fixed. Their interconnection is fixed. FPGA chip, you again need to make that, fabricate that chip. Okay, fabrication is common with both of them. But once FPGA chip is designed, it's designed such that the it has different building blocks on it. Now I'm talking about FPGA. FPGA has different building blocks. Okay, and as a user, you can buy one FPGA board. or you can buy one FPGA chip, create your own board, put it there, and you can, through a software, it's a different software now, you can create a hardware on that using software, like in a languages like Verilog, VHDL, System Verilog. And you can say, okay, I don't need those 30 million flops. I need 10 for my design. I need 10 million. I need 1 billion flops. And I want to connect them in such a way that, okay, with my, I want to change the hardware, their interconnection. You can do that. No, you cannot change everything. Only the flexibility that that FPGA vendor has given you. Okay, so they are making the chips that, okay, we will need to make certain building blocks, and user may want to use some of them and maybe want to connect them. They have some sort of matrix they're connecting. So what happens is eventually this is an FPGA. Okay, this is Xilinx, which is bought by AMD, I think I know. So this chip, you connect to the cables to your computer. You create a new hardware, and through those wires, you can do ones and zeros stream coming in a way. There is circuitry on FPGA that it can make or break certain connections. So it connect them or disconnect them, and based on that, you create a different hardware. Understand that? But the common part is somebody need to design and verify and fabricate. Somebody need to design, vary, and fabricate. But once hardware is done, programmable through software. But this is where you can really change the hardware. A6, Intel makes its A6 chip, i9, i7, goes into millions, right? So this step is very expensive. And we'll come to that in a minute. But FPGAs are not good because flexibility comes at the cost of something. Flexibility, it's great for like smaller design. You can prototype, but its speed is a limit, and the power is more because there's always component that you're not using that take power, right? Okay, and by the way, we can also have ASIC that has small FPGAs built already on them to give you the more flexibility. I intentionally brought FPGA because this is where this can be very useful thing for you guys because they are cheaper. So chip industry and engineers forget about this. It's a business. Okay, and for a business, you need a sellable product. And for that, you need clients. You need somebody who can buy your product. So you have an idea that of a chip, you search your market, and then eventually you need to sell it for a price. And here are some of the things that are not taught to students. Okay, simple thing. So when you create a product, you have your own cost, right? And then you sell it. And the difference between price and cost is what? Anybody? I gave a hint there. What is this? Write your whatever you think in the chat box, and Abiha, you can read that. The difference between the cost of a product, cost is actually how much money you spend from your pocket to build that, and then you sold it. And what is the difference, Car? Anybody? I'm
There
giving.
some students said gross margin.
Yes, gross margin, gross profit. Okay, so that is your net income from that, right? That's why how much eventually you're gonna bring home and pay your bills from. So the cost is what typically? Now it has fixed expenses, variable expenses. People who are doing business would know this, but typically I just simplify here. You need to spend money on marketing, right? You need to bring ads. You need to um, show posters, or you need to give freebies, and then you need to spend time on, okay, prototyping. You need to make some for your own design, right? Even the chip is used. You give eventually to Google or YouTube or those Meta, but you need to test it yourself. So you need to create a board, put a chip on it, and run and everything the way your customer is going to run, right? So that is prototyping, and you need to hire people, right? But let's talk about the design cost where we come into the picture. So design is you have a hardware and you have a software. Okay, I'm keeping software aside, right? All Intel chips will need to have some software written, and every chip will have some sort of software. Gives you flexibility. Software is super important, but we have hardware people here, so I'm going to talk about hardware. So hardware, you have three things. First is you need people to design. Then you need tools to design because this IC designing is a very specialized field. You need to simulate things. You need to create a layout. You need to prepare database so that you can send to fabrication and then actual fabrication, manufacturing. So in the design, you have three elements. Oh, that's good. Should have done before. So HR, you need
Okay.
to, sorry.
Sir, I'm sorry for interrupting. I just need to make a quick announcement for the participants.
Sure.
The e-certificates will be provided to everyone attending today's webinar. You just need to fill the form for it. Thank you, sir. You can continue.
Oh, no, no problem at all. Yeah, that's exciting. You guys gonna get certificate. Cool. Okay. We have 15 minutes. Any question by the way so far? Anybody ask any question there that I can take right now? No?
Sir, there's a question. Which software or course should we learn related to these chips, or which would be beneficial for us, for me as an electrical engineer?
Oh, okay. So for you as electrical engineer, I think looking back over the career, there are two areas for learning the languages. Um, One is the pure software, right? For example, you are building um, a software that is going to run on some CPUs. So it's a C plus higher level language, which you know is converted to assembly language, and assembly language is converted to machine language, right? Computers understand machine language 0101, but in assembly language. On a bigger CPUs, we don't write in assembly language. So the assembly language is very sitting very close to the CPUs and instructions. I should teach you guys maybe computer architecture sometime. But okay, next one is the C higher level. Okay, one area of software is that you create software that's eventually going to run on CPUs, and this is purely software field, right? You're creating apps, you're creating applications. That is one type. You guys as electronics are probably not going to do that, right? Um, there is another aspect of um, uh, software is also maybe interacting with the assembly language to understand what's happening on a computer, like a computer architecture level, right? So that helps. That can have applications where you understand the CPU architecture better. I think that's the advantage of that. There is another type of software which is really important for all of you who are going into chip design, and that comes around scripting. Okay, so even though we play with all these IC design tools, in order to run simulation, in order to check things, in order to generate data, in order to verify even in physical design, we need to script a lot of stuff. We want to automate things, right? So when it comes to automation, we rely on, okay, here's the thing, you guys, when students come into industry, they don't know the shell, right? You're familiar with the GUI, graphic user interface, but you're not familiar with the Unix environment. So Unix shell scripting is very important. It's very simple. That's very important. Second thing is you need to know some other languages such as Python is very common in the newer generation that comes. I do a lot of coding in Perl language. You know, when before Python, Perl used to be very famous. I'm still in code in that one. Okay, so Perl, Python. We don't use C, C++ a lot, but if you know, you might have some advantages, especially if you go to EDA. There are companies like I work with Cadence. There are engineers who create software. They write in C, C++. So sometimes it can be advantageous for us too, but a lot of, as a chip design, you will work on shell scripting. You will learn, rely on Python or Perl type of languages. And then there will be languages of the tools, like Tickle is used in Cadence, Synopsys, probably in Siemens as well, right? So knowing those languages is super important for you, but they're not tough. Once you know one language, you know that, or you can easily learn other languages. Good question. Any other question I can take? Okay, nothing. So we have 12 minutes. Uh, yeah, you want to say something? Go ahead.
So there are a few more questions.
Okay, yeah, great. Go ahead.
Uh, Kindly share some research-based FIP for the third and final year, specific to the designing side. I'm doing
Oh,
electronics engineering.
oh, you mean final year projects?
Yes, sir.
Okay. Mm-hmm. All right. So again, that is a lengthy answer. There are different things you guys can do. I think that's where I was heading. So give me 5 minutes and then I finish this and then I will touch that too. So and I'll go quickly a little bit. Okay. So tools we use Cadence, Synopsys. Most often these are the common ones. Siemens EDF, some very good tools as well. So manufacturing we use TSMC, which is foundry. Now, Intel is design and foundry, so it has a unique position. Samsung foundry, it's a independent, not Samsung phones. So global foundry. So we use fabrication plants, these foundries, who provides us a technology, what transistor technology. The latest is 2 nanometer, 3 nanometer. And what are those is typically indicated as the length of the transistor. So this costs in millions. These tools cost in millions, and people, expertise and expert people, it costs in millions too. So I want to show you quickly. So when it comes to designing a hardware chip, um, what are the different departments? And this is important for you, even to relevant to that questions where you can go into. Okay, so at high level, we start at an architecture level. Okay, okay, for this chip that somebody in marketing figure out that would be great to bring this chip, or having these features on this chip is really important for you to be in AI market, be successful, right? This speed, this power, this sort of area, and these many PCI, these many CPUs, GPUs, blah blah blah. So then microarchitecture people, they convert architecture into lower level kind of building blocks, different hardware building blocks, right? Then comes these people RTL, work on register transfer logic. This is really those people which eventually, these breadboards you might have seen, probably still work on those. So these are the people who convert microarchitecture, different hardware components. They create hardware for that, and they use higher level hardware languages, which are software. So you create hardware and software, right? So system verilog, verilog, VHDL. Once that hardware is written there, they simulate and verify that. So it's RTL design and validation. And this is mainly all those system verilog thing. And then this comes physical design. Now you're not creating, eventually you need to create transistor, right? So somebody need to convert this RTL higher level hardware description into transistors. And that is the job of this physical design team. So for analog, it's a little bit different scheme. Analog design testing methodology is a little different, but predominantly you are here in the digital area. So after PD physical design, you'd create eventually a transistor-based database. Then that you call a tape out. So Before, in older time, there used to be actual tape that you send it to fabrication, but still that's the same terminology. You just, email or just push a button and database is sent to the fabrication. And they fabricate it. They take a couple of months or 2 3 months to fabricate this whole thing. Typical cycle for this one is a year to 2 years. Okay. And then once the chips are back, you verify that you really they work the way you wanted them to work, right? Um, all right. So in terms of careers, for you guys, um, this is the best. In Pakistan, we don't have that many companies doing physical design. This is my area of expertise. Okay. And with my YouTube channel, my goal was to actually spread more of that knowledge on physical design. Um, but for you guys, it's best to enter here. And that's how I entered into this field. FPGAs give you a very good way to enter because the programming is done in system Verilog or Verilog VHDL. And this RTL is for ASIC is done also in those languages. So the person who is really good at eventually can come here and contribute here. So I started my bachelor thesis, final year thesis, or project you call it, on an FPGA. I took a codec and implemented on Xilinx FPGA. And then there's a company enabling technologies. They were developing their ASIC, so I went into RTL validation. So after that, I went for master, and then when I finished master, I went to Germany, and that's where within Intel I started working in physical design. Within physical design, a lot of things there. I don't want to go in detail, um, but right now, even there are some companies in Pakistan, the local startups. There is a lot more work happening here. There is some work happening here as well. Okay, so if you ask me, okay, how you want to prepare yourself, so I have a YouTube channel, and my goal is to it's a digital ASIC design course, but I prepare for physical design. But the path, these are important things I've written here. So at your level, um, in tuning the bachelor, you need to be good at this thing, right? Or what is this? Um, how to build a digital design to solve a problem. You all have read logic design and all that, but if I ask you, okay, I want to design a traffic controller, those are green, red, and yellow. I want to create a controller that after can change the traffic lights. Can you create that system for me? That is a problem solving. So for that, what I learned, even when I did my bachelor thesis, but now looking back, I think my understanding how to create a hardware to solve a problem, how to design a system, digital system, a binary logic design, which consists of combination and sequential, how to create that. And you guys don't need an actual, you can create it on a system Verilog or Verilog VHDL and simulate that on software. So that is even on my YouTube channel, I focus on it that I want to make sure people understand this component. And then comes eventually, this is not what you're going to send to fabrication, right? Fabrication is a transistor. Now, this thing, I remember even my bachelor, I didn't like this field because I think transistor is not taught well, but transistor is fun, I can tell you. So then I focus on making sure students understand CMOS transistor. What is CMOS? What is transistor? How you create inverter with transistor? How you create AND gate with transistor? How you create flip-flop with transistors? Okay, what is the technology? What is 2 nanometer, 3 nanometer? How the scaling works and all that? And then I work on that. And then at the end, I go in deep into physical design and all that. So back to that question. Sorry, I took a lot of time. This says you need to focus. You learn this and have some good idea of this one. Focus on these type of projects. It's best for you. So yeah, sorry, go ahead and ask. Only 4 minutes left. I have another meeting. Otherwise I could have stayed with you guys for longer. But we can do another follow-up session where you can ask me question based on this, and also give you some idea on, okay, what skills you need to have, what, how you can be successful in future, and some of the learnings from my career as well. So I would love to share those with you. But yeah, we are read more questions. We have a few minutes. Are you there?
Sir, one of the questions is, when do you think AI or AI tools will take over the chip or IC designing for both aspects, digital and analog?
Okay, yeah, it will take us a while. Yeah, people are trying to get into RTL design. Um, and that, okay, instead of hiring RTL engineers, you can write it. I think there are some companies. There is some success, right? So I know. I also think RTL is the best way, is the entry point for AI to automate things. Um, but I think since chip is so critical, right? Um, Verification is another area which I think AI will have a lot of RTL validation I'm talking about, because validation takes a lot of time. So I think AI will penetrate initially into those areas, but it will take some time. Chip industry, as I said, it takes millions to fabricate something, and if you miss something, it's might be the end of your company. Um, so it is very critical. In physical design, the Synopsys, Cadence, for example, even in their tools, they're trying to bring AI things. For example, instead of you run so many experiments for different, changing some inputs, AI can run it. Those are good for some experimental runs so that you can decrease the area, you can increase the performance and reduce the power. But it's not getting that much traction yet. So I think for chip industry, it will take a while. Now, where is very helpful today, I was creating some scripts there and automating few things, and I make use of ChatGPT so much. Okay, I'm doing this. Can you generate this automation? Can you do this scripting? So it is helping a lot to designers in that way. I used to spend days on creating scripts. Now I spend hours because I get a lot of help from ChatGPT.
Yes, sir, there is another question from Ahmed Salal. I will unmute it.
Yeah, what's the question?
Yes, Ahmed.
Uh, Assalamu alaikum, sir. So I want to ask, what is the purpose of microcode in processors? And basically, we need a software above that to control the processor. And then, what is the purpose of the microcode? And please tell us about the recent exploit in the Intel chips that was, I think, patched through the software. I think Meltdown it was called. Thank you.
Okay, so I don't know the specifics of that, any meltdown and all that. Honestly, I was with an Intel on the data center side, and even if I was on the client side, I don't think I will talk about it, right? But I give you um, a generic answer for that. For first, your question on microcode. So your one thing is your um, microarchitecture is in the same way that, okay, so when you talk about CPUs, you talk about instructions. Okay, your CPU can run what kind of different instructions, and what instruction are supported. And for instruction, there is a machine, then you convert into machine language. So I don't know if I understood your question properly or not, but as a embedded engineer, as a device driver engineer, yes, you get to work with those. As an architect, you get to work on those things as well because you're creating your instruction set, right? But I think as a chip designer generally, especially if you are in RTL in designing, I think you tend to, or a higher level, you tend to use it. But where you guys will come into the picture, most likely you're not gonna do a lot of that one. But as a software, because even in software, I remember with Intel Ireland I work, there was a lot of software engineers, and there were software electronics engineers working on creating device drivers some low-level software for that. So that can have some potential for you to work on too, if you some of you really want to stay with more of on the software side. Again, it's RTL coding, validation, and verification and writing is also um, very very much software. So you can still be on that side if you like that. So I don't know if I answer your question, but what we can do, Zan, or we can do another session. I have to go into another meeting. So it was wonderful talking all of you, and I will see you in another session pretty soon.
Thank you so much, Sir Rashid, for your valuable insights.
All right. Thank you so much. See you. Bye.
Yes, thank you,
Assalamu
sir.
alaikum.